Well, welcome to our first structural modeling video conference for 2017. We're going to be covering some new approaches we're going to take this year and some new ways that we've been handling things. The agenda should be up. The current agenda essentially is going to be one of the things that we're going to change just slightly. And what we're going to change just slightly is we're going to have kind of a running appending of the agenda, so that we're going to have the current agenda at the top, but then leave the other agendas below, so that you can go back and see where specific subjects were addressed at what time. Get a better idea of focus on that. Hello, Peter.
Hello.
All right, so we've got a sound check with Peter. Things are good there. So what we've done this year and what we've started doing is the read ahead we posted as a technical document on ResearchGate.
Good idea.
And Mary, would you like to explain that a little bit?
Sure. We decided, partly based on questions by Peter and Janet, to try to provide a document that covered at a high level the work that's been accomplished for the last year and a half when we actually started on the structural modeling project, as opposed to the basic structural modeling project. And then towards the end of that document, which is probably 23 to 25 pages, which is a lot longer than we will be doing technical documents from this point forward, we actually start capturing the things that we are proposing to talk about, which are now included in our agenda. At this point, we are also planning to issue some appendices to that technical document that capture the agendas themselves, the emails that have been sent out for each of the different conferences, and also the minutes that might have been distributed in addition to those videos that are already online. So that way everybody will have one way to go and find it. Hi, Janet. Happy New Year. Back to you, Joe.
Okay. So late last year, we took and concentrated our effort on putting out a few web applications to demonstrate the processes and procedures of the structural modeling activity that we've been going through. And we produced 3 versions of that software. And the first version was the Seagull software version that we presented at the Seagull Open Source Software Conference in Seattle in November 11th, I believe. Kevin was helped present to that conference remotely. Also, Thomas helped present at that conference. He was there also. And what that specific piece of software was is envisioned as using that to help a person that wants to explore the algorithms and how the algorithms work in the structural modeling system. And really what we've done is we've taken the algorithms that we've found in the Handbook of Interactive Management. We've taken those and started to look at those, but the logic within that system is driven by the human user. So there's no embedded type of logic in that one. The system just does what the human user is, the algorithm the human user is putting in and testing. So that's really like an algorithm test approach. The SMP Phase 1 software version that we have out there, the next version, what we've done with it is we've taken the Seagull version and just updated it a little bit so that the scanning for the upper triangular piece and the swapping, which is manually intensive and fraught with errors unless you're paying a lot of real close attention. What we've done is we've automated that portion. So this SMP phase 1 software version, the algorithm now, most of the algorithm is still input by the human operator, but the actual part of going through and swapping and making sure that everything within the matrix, the greens are in the lower triangular, the reds are in the upper triangular, that is now done automatically by the software. And then we have the N1 version, which is the main development thread on ResearchGate, and it has the clustering algorithm is now complete, and it's driven by an internal algorithm, and the software just asks you questions, and you answer those questions, and then the software itself completes and essentially presents the same outcome as in the Handbook of Interactive Management in the clustering method, or the clustering command. So that's kind of a brief overview of what we're doing there with the software. We've also established a new, well, not a new, we just decided to focus on the structural modeling Google Groups list, so that people that are interested in what's actually going on with the project should sign up for the structural modeling Google Groups list, because that keeps track of all of our information. What we found when we went back and started pulling things together is that hadn't been very disciplined in the way that I've been communicating, and it was difficult to find all the places where things have been published. So we made a decision then to just focus on the structural modeling Google Groups, who have the main piece of the information, and then we'll provide announcements and things other places, but all the information will be on the structural modeling Google Groups portion. So is there any questions with that so far? Okay, I think we're good to go with that then. So there's been a couple of very interesting things that have happened, and one of them is the insights that have come from actually doing the software algorithms from the interactive handbook. And what we found there was some things that are common, but there's also some things that are very different about the software approach that we use to create the software. And a main topic that the team needs to focus on is what is a test case for the complete type of software that will do everything. And when we say do everything, that's kind of a very vague term, and we're going to make that term more specific going forward, and especially next month we're defining a very specific approach to definition of what we mean by everything, what are all the different approaches to solving these types of structural modeling problems. And as part of that, we'll need to further develop the concepts of the global, local, and relationship precision. The AMEI helped us focus on relationship precision, which is really benefiting our definitions going forward. The local and global ideas, then, those are attributes of a relationship that help us select a solution approach. And when we're doing that, when we're looking at the solution approaches, we really have many cases, we have some semantic complex between the mathematics, or the strict mathematical definition that we're covering, and the natural language definition that we're covering. So those are generally what we're going to be doing going forward. Did anybody get time to take a look at the read ahead document? Is there any questions, or should we just kind of go through that briefly, kind of give an overview?
Well, I did get a chance to read it, which fantastic effort. Thank you very much. Very, very helpful.
We agree on that. We also read it.
Okay, good. So we had some good. That's excellent. It's just to start.
And you hit on the two things or a couple of things that I think I was going to ask you about. One was, the articulation of the relationship types, as you mentioned, and it's interesting to hear that that was sort of like an emergent property of using the particular programming approach that you took. And I think the other thing that was helpful, that probably needs more, as you say, you're going to focus on, is this difference between the mathematical language and the natural language, or definitions, and that's helpful as well. And also the global and local piece, I think, is very interesting.
Joe, we have a request here from Kevin Dye to go through it briefly. So perhaps as Peter winds up with the things that he was interested in, you might just go through it in particular to those questions.
Well, then, yeah, and Janet also had some comments. So why don't we get the comments first, and then we'll go through it. That's great. Go ahead, Peter.
Well, that was it, really. Those were the points that I think came out for me. And then a sort of request at some point is that that as you've articulated it clearly there. I mean, I don't understand everything in it, obviously, but I'm sure in time that will be true. I would appreciate some help really understanding the relationship types, particularly the definitions of things like transitive, and maybe that's my own ignorance of some math that I need to be aware of. But that and then the whole measurement of relationship type is something that I'm really very interested in too. You've got it almost in a sort of binary, either is equal to or is not equal to or is a precursor to, in terms of sort of almost a sequential logic. Is there any way to think about different degrees or percentages of relationship?
Getting ahead of us, Peter. We're going there.
I know you are. But thank you very much. Just tracking that we're on the same. We're reasonably congruent. Okay, so I'll shut up now. Thank you.
Yeah.
Kevin is chiming in on Peter's comments. He's saying in the December meeting, Peter asked about the mapping from natural language to the formal language, the logic. And he says, as Peter was finishing up, he says, I want to address that question.
Cool.
So who was it you said that? I missed part of that.
Kevin Dye.
Oh, okay, good.
He's online, but he can't speak. And so he's chat.
Okay. We have some things marked up in here. We have some questions, some just suggestions of phrasing for clarity. But I don't know if we want to take our questions as a group, or should we step through page by page and we can address things as they come up?
Well, I think it appeared to me that Peter's questions and comments were very general, and I think what I hear you saying is you have very specific comments.
Right.
And so maybe what we can do is let's just kind of start walking through it now.
Okay, that's a good idea.
And the purpose of this, of course, is to bring together and try to start mapping the conceptual space and identifying the major big pieces of things that we're going to have to agree on their names and how they interact so that we can move forward and make some clear distinctions. And so I'm glad to hear that people are talking about refining definitions and just working through it. So I think that's really great. So the introduction piece here, let me get to the right part. So essentially what we're doing is we're focused on reducing complexity. I'm going to reduce complexity by reducing uncertainty. So we've talked about, in general, these types of system complexity reduction activities that Mary and I have developed and basically communicated either through journal papers, tutorials, conference presentations in the last couple of years. And essentially, what that breaks down to is it breaks down to the idea that we need to clearly understand the items and the concepts in context and be able to communicate with those of other people using these isomorphic relationship and the three language components: prose, structured graphics, and mathematics. So we gave the key definitions. Walk through those. Were there any questions about the definitions at all? Okay. Then what we did with the historical content is we just talked a little bit about Warfield's framing of the structural modeling, the two components. Then we added the third component so we could specifically talk about putting things in the proper context. And that's the graphic for that particular part. And we believe that we can get a tremendous amount of uncertainty reduction and therefore get a tremendous amount of complexity reduction, focusing on the methods, clearly defining the methods and techniques in the structural integration area. And what our vision of how these things generally fit together in the big parts is that the natural language relationships and the natural language approach and verbiage comes from the interpretive structural models that are developed in the real world. These are domain experts engaged in day-to-day interaction with complexity. They're using the natural language. The basic structural models, the formal semantics of the mathematics then are associated with the BSM. And what we need to do in the SIM is clearly define the methods and techniques that we use to make sure that these are put in proper correspondence, are properly aligned, and make semantic sense. So that's basically the goal here. And we're outlining the components of that based on these three high-level parts. We talked about the reduction of uncertainty, the Combs filter, which is a little bit different type of uncertainty reduction. We may use that later on in certain specific types of structural modeling. We haven't applied it here completely yet. Structural modeling, of course, automated n-squared charts, which come from Hitchens, and we've adapted those a little bit to kind of start coinciding with the ideas of the structural modeling matrices. The abstract relation type, which requires the three types of languages, and the automated model exchange isomorphism, which allows us to start specifically talking about kinds of systems.
Can I ask that you are sort of, I mean, I love the ART framework, and do I assume that you are having a little bit of fun with that word?
Well, the abstract relation types, there was actually, so from a computer science standpoint, they have abstract data types.
Right.
And so I looked at all these formalisms, and the abstract data types, they're basically methods of how you deal. They're general types of abstractions
Right. But I mean, I just thought it gave me a new insight into art.
Well, basically, so I'm focusing on the definition of a system, right, as a relationship mapped over a set of objects, right?
Right, but
And so,
they could be paintbrush types or pixels as well, of course.
of course, but you see the real, you want to know the real reason for the abstract relation type name is I want to write a book that's called Abstract Relation Types: The Art of System Science and Engineering.
Ah, okay. Thank you very much. Lovely.
So if you're looking for the real reason,
Yeah,
right?
I was looking for the real reason, yeah.
But fundamentally, we need to focus on relations because relation and relationships are the most advanced way we have to define things.
No, absolutely. No, it's wonderful. I love it. Thank you.
Okay. All right, so that's that part.
So just a comment on that section. It's very rich, the reduction of uncertainty. There's a lot there. And so this is the section where I think you could improve the framing, because you start out with 5 methods and then you have 6 methods. And so you're using the same word, right? 5 methods for 5 general examples and methods to evaluate complexity reduction capabilities. Anyway, so the somehow maybe with a graphic, I don't know, but or maybe with different, just adding some extra text there.
I see. We overloaded the term methods here. In
right.
This, got it.
Very close together, right?
Good catch, Janet. Good catch. I didn't notice that. Okay, we'll make a note of that. Next version, we'll address it. Let's see. Yeah, it's we really didn't. We've got to get these out and get them discussed and get them documented. Okay.
Another thought that just came to me in that regard is this term structural modeling.
Sure. Yeah.
What is not structural modeling, to invoke the spirit of Jack Ring?
Well, process, right? So systems, right?
Okay, all right, okay. Process modeling. Okay, so
yeah, because if you look in the giant domain of systems basically you can view them as having structure, or you can view them as having process, right?
Yeah, absolutely, sure.
And
I mean,
so
Chesterfield talked about the difference between, the process and the structure being the climate that you are experiencing.
Right, and so that some people say that the difference between that, is architecture, right? And there's a book that's called on architecting. It's called "Why Eagles Can't Swim."
Okay.
Right? Because they don't have a structure to swim. Right?
No, Kevin's also contributed here that the first set that Janet had mentioned are not really methods. He's indicated that anything that lacks a logical basis is not structural modeling.
Okay. Right, and so that's a very good point. And
you might want to add in a introductory paragraph on these points, because that's also helpful context.
Right. So okay. So and this is kind of was a decision, and we've made in presenting the material, because what Kevin has said about logic is correct from the classical point of view. But as we're going forward, and what Peter was driving at, and some of the things that we're looking at, is that there's also basically the idea of processes and the selection of different processes and causation within these concepts within the system, which are not necessarily, you can't logically compute those. Those are information-based selections like you would use with an intelligent agent, but they're mostly confused. The terms are, and so my plan was next month, I'm detailing a very specific area on the reachability matrix, which is kind of the core mathematical piece. I was going to use that example to start motivating these differences. And so I decided not to put it up front because I didn't have any examples to really base it on yet. So, Janet, what we're really planning on doing is it'll be kind of not well defined up front, but in the next sets of technical reports, as we develop more concepts and information, then we will refine those concepts. And then once we do that, maybe then we'll go back and put them at the top. Does that make sense?
Right. Yeah. Then maybe just one or two sentences up at the front, and
Okay.
and a reference to another technical report or something like that.
Well, when it's written, that's in the process of
Right.
right? Okay. All right. So that's kind of what we're doing here. So essentially, what we found was that these 6 items, methods that are really foundational for complexity reduction. And the 3 language types, when you have to take the effort to go through and to map an informal language to a formal language, like informal speech to logic and mathematics, right? Then we have some very, you have to think about that and be very clear about the relationships, and you define that system for that definition, and you reduce a tremendous amount of uncertainty just doing that.
I hate to sort of keep, stopping you in stream here, but, the other thought that just occurred to me with this is, on your team or in your circle, do you have anybody who is parallel tracking this, who might be Chinese or Indian or Hispanic?
Well, I'm really not sure who's reading the material out on the internet. But
Joe, the one person that occurs to me is Alexander.
Right? Yeah, Alexander's reading it, but what I think I hear Peter asking is, do we have a non-Western philosophical worldview person looking at this?
Well, yes, and the English language in the way that it's what just triggered that thought was when you were talking about mapping of informal language to the 3 types.
Right.
And I was just thinking of how you would map that if it was Chinese, or if it was Indian, or Japanese, as a for instance.
Right. So in the 70s, I believe, and Kevin can correct me on this if I'm wrong, but I believe in the 70s, the Japanese
Kevin has contributed something that might lend a little bit to this. He said that on this second set, in other words, the questions that we're talking about at the top of the page, we can note the advance on previous work. I think that it should be noted that although Warfield spoke about the relationship of natural language and formal language as being contextual, very weak in depicting that mapping, and poor in the empirical basis of the psychology of the relationship and the word.
Right. So those, I believe that area needs a tremendous amount of strengthening, and I agree with what Kevin has said, and that needs a lot of work. And so that's what we're doing here. And hopefully, Peter, I think that an example of how this has been used in the past was the people in Mexico used this approach where the dominant culture was communicating with the indigenous, with quote unquote illiterate people that didn't speak the dominant culture or know the dominant culture language. And they used the structured graphics and the mathematics to actually co-develop a kind of quick language that they both understood in that event, right? So that it helps to generate immediate understanding between two groups that have some way to get connected with the formal mathematics or the pictures. And it kind of reminds me of a person that here in the Pacific Northwest that studied the languages of the native cultures up and down the coast. And the takeaway I got from that study was the fact that there was many different languages, but there was a core set of words and a core set of concepts that were common among most everyone, and they were the common things like food, water, shelter, things like that. They had this common set of things that you could use to almost immediately get by and survive. And then when you got into a different tribe or a different subculture, then you needed to use those things to be able to figure out what the local context was.
Yeah, I mean, this gets to the global local piece, and I'm particularly concerned about it or interested in it as we develop our notions of what systems literacy might mean in a global sense, because we've already run into problems with the word literacy. And I'm now just reading and listening to Tom Wolfe's Kingdom of Speech, which you might find interesting, and as an aside, where he puts in some context Darwin and Wallace and Muller in the relation of language to evolution. And I know that's another digression, but I'm just thinking about the universal application of this work in a global context, and in particular, application might be, the determination of what global system literacy or fluency or awareness might be, as a specific application of the work that you're doing in helping to bring that forth.
Well, it is interesting, and we hope to start giving specific examples. And so the technical report number 5 for next month, we're going to have graphics, but now I'm also going to insert mathematics code that will run in at the Sage Math tool from the University of Washington. So I'm going to now start trying to use all 3 of these forms in the definition pieces, so that we'll have a prose definition, we'll have a graphic representation of the definition, and then we'll have the mathematics of what that means. And start that next month, and we'll try to go forward with that and see how well it works. Okay, so then the framework for logical properties, the augmented model exchange isomorphism. This basically just used for a complete topology of all the combinations of the primary logical properties that we find useful so far. We have found some logical properties to not be useful, so we haven't used them yet. And then we go through and try to figure out what the logical property set that Warfield was using. And as Jana pointed out from the binary matrices and structural modeling, at one point he says, well, it really doesn't matter if they're irreflexive or reflexive. It's kind of convenience. That's kind of a lot of uncertainty there. So what we've done with the augmented model exchange isomorphism is we said, well, we have all of these particular combinations, and you need to choose. I mean, it has to be one or the other. It can't be everything, at the same time. That's just, logic doesn't work that way. So we primarily then developed the MEI to allow us to give specific unique names to these logical categories, and then start mapping their mathematical and natural language properties to each other.
And any pointers you've got to help me understand more the reflexive, irreflexive, symmetric, asymmetric, or transitive, intransitive.
Okay, so
If there's some references or something, I think that would be helpful to me. I don't know if it's Warfield, if I need to go back to Warfield.
Wikipedia should have good.
Okay, all right,
yeah.
thanks.
so it's okay. So it's a type of logic. It's prepositional logic. That and what it does basically, Peter, I think the main thing for me that helps me when we're talking about these three things is reflectivity is associated with only one object. Reflexive, that's whether it connects back to that object. There's no two objects involved. Reflexive is only one object, okay?
Okay.
Is between two objects, right?
Right.
So reflexive property is only assigned to one object. Symmetry is just between two objects. And transitive involves three objects.
Okay, got it. That's helpful.
And I'll send you a link to a couple predicate logic books that basically explain it very, very well from a natural language argument standpoint.
Thank you.
Of how these work together. Now, the transitive component is interesting in a number of different ways because mostly in the graphics, you never put the transitive connection in because it would just flood the graphic. And this is something that we're going to need to determine the best way for us to represent these concepts. But just for starters, right? Reflexive is one object, symmetric is two objects, transitive involves three objects. And then we've given them names, right? And so we say, well, okay, if the four green boxes are the ones that Warfield appeared to use, and that could be cut down to two of those if you only use reflexive or irreflexive. So you could have anywhere from 2 to 9 of these specific, unique identifier logical property group types associated with Warfield's work, depending upon how you interpreted what he was saying. Because he only used transitive, he didn't use intransitive or non-transitive. These other 18 groups weren't included in his work.
Joe,
So, yes.
Joe, Kevin has indicated here that the correspondence of a word representing a relationship and whether the belief of the user of the word behaves consistently in a particular logical fashion, i.e. holds to a relational property, such as transitivity, all of those things, is an empirical matter.
Right. Okay. So that's empirical matter from the ISM real world point of view, where we were doing that, right?
Right.
That's absolutely true. But these words have maps, or they have basically pairs in mathematics, in matrix math.
Kevin provides an example. For example,
Sure.
Friend is not consistently transitive, but trust is more so.
Well, right. So these are very important natural language relationships. And that's the way humans think about it. When we start transitioning from natural language, put it in proper correspondence with mathematics, right? That's when we need to think about what these things mean. So I agree 100% with what Kevin's saying. What we're working now is what's the proper way to integrate these.
Right, and I think it actually is, articulation is another word that you should make a lot of use of, because what you're doing here is you're articulating all of the possibilities in order to reduce uncertainty. And so it's very important to articulate the mathematical relations separately from the natural language relations, and then to understand the possible relationships between them.
Oh, you're right, Janet. I think that one of the things that really impacted some of the things I was reading was Kowalski's work on where he talks about natural language, deep logic, and the world. It talks about the different types of logic that can be applied. And so we, and in that process, he does a couple of things. The first thing he says is that adductive logic mostly is confused for causation when people start working with it. And causation and abductive logic are different things. The other part, he says, is in abductive logic, mostly you can't prove it. You can't take that logic and calculate a type of solution, so that you need to have process rules. And so he talks about the confusion between process rules and logic just from this area where he says, well, we use process rules by really reducing conflict and reducing the conflict between these two. And then we use logic, we can basically compute what the answers are. So hopefully we're going to go into that in much more detail as we go forward. So appreciate the comments. Let's see. So then we talk about the problem with the adjacency matrix model, some of the confusion there that was going on. And then again, we give the complete categories of the AMEI and what they are. Okay. And we talk a little bit about why we don't use a partial order. At this time, we may in the future, but right now we find it generates too much complexity because of the uncertainty. Talk about the natural language use and the mathematics use. The local and the global. This one, what we're really trying to do is talk about a relationship that maps over everything. And geometric position, I think, is something that maps over everything, where the idea of like influences doesn't map over everything. So we have the idea that a local relationship just acts between two objects, and a global relationship acts over all the objects that are a subject of interest in this study. We did the object-based cluster and the space-based cluster as an example of these. And so we talked about, in the clustering parts, and we've mostly been working with the asymmetric types of structures. When we get to the symmetric types of structures, we'll focus more on clustering and the type of techniques we can use for that. Okay. And then we talk about the minimum number of objects for system design mode and system discovery mode. We'll be presenting a paper on this at CSER in March, a little bit about what this is and why it's important. And we have the open source web applications I talked about briefly earlier on, where those are, what we're doing with them, some of the insights we've found from those. Gives the links to the software where it is on GitHub. If people want to work with that, they should probably let me know so that we can, so I can give them some of the updates. There's a couple of updates I haven't got out there just yet. I hope to get out soon. Okay, please talk about the minimum number of objects for discovery modes. Exit. Okay, so essentially, what we're doing here is the figuring out the minimum number of objects you need for discovery mode. And if you look at this, you'll find they're all 4, minimum number. And the reason that 4 was selected was that you need to be able to know that what the transitive component is. So if we were just talking about the reflexive component, we'd only need 1 object. If we were talking about the symmetric component, we just need 2. The transitivity involves 3 objects. And there's 2 types of transitivity. There would be the type of transitivity that has just 3 objects, or there would be intransitive, which says, oh, I don't interact with any other objects. Or there's non-transitive that says, well, yeah, sometimes I'm transitive and sometimes I'm not. So you need at least 4 objects to be able to determine which one of those you are. If you're transitive, it takes 3. If you're non-transitive, it takes 4. And to know that you're transitive, you have to know that you're non-transitive. So you've taken 4 all the way through for the discovery mode. This is where we're going out and discovering this information. So hopefully that clarifies a little bit. It's the transitive component, and then you need 1 extra to determine whether it's really transitive, non-transitive, or intransitive.
Can you hear me?
Yes.
Okay. Yeah, we lost power here. We're going through an atmospheric river event. So we got on iPad on cell. So
all right.
Yeah. So I missed a number of things that you said. So I don't know if you talked about for Peter, if you look at these relationships in node and edge graphs, that's where you can really understand what Joe was saying. Very helpful. The reflexive would mean that you have a loop. Each node has a loop going back to itself, and symmetric would be whenever you have an arrow going one way between 2 nodes, you have one going the other way. And then transitive says that the relationship holds, as I imagine he described, among successive relations.
The AMEI has all of those pictures,
right,
associated with each one. So if you look at the AMEI and read that, you see that. And I think the lines and the logical properties are also color coded, so you can see it on the AMEI. All right.
Let me see if I can catch up here. I did have a question. Okay, on page 6, the natural language relationship adjacent to is not transitive.
Right.
Could you explain that?
Oh, sure. So if we have, let's say, 6 houses in a row, right? And they're, house 1, 2, 3, 4, 5, 6. House 1 is adjacent to house 2,
okay.
but house 1.
Okay.
Got it?
Yeah, got it. Directly adjacent. Okay.
Right.
Okay. Then where are we on the? You're on page 10. Let me see if I have anything else before then.
We're on page 11 at this point.
What's that?
We've just reached page 11.
Okay. So the right. So the issues about preceding and the fact that the mathematical relations are odd when that they use the words differently, the preceding and influencing and that kind of thing, but where something precedes itself, but that's just by fiat in mathematics. It's like saying that, defining that any number to the 0th power is equal to 1. That's just defined by fiat because it's useful. So I think it as long as you're articulating the difference between the mathematical use of the language and the natural use of the language, then I don't know if you need to, is this where you talk about defining connected to, or is that?
Right. So what we did for what we talked about is also some uncertainty about the idea of adjacency matrix being associated with a graph. And so that what we said was that essentially the connected to we used instead of adjacent.
Oh, I guess that's later on, so you'll get to that in a minute. So let me kind of catch up here. Local global size. What's that?
You're fading out a little. We can't hear you.
Okay. The local global, I don't grasp the idea there. I can appreciate the pairwise object-based versus space-based, but I'm not sure how what the significance of it is.
Okay, so that's what we have here. Let's say, for example, let's take a global relationship, a relationship that has a global property, and let's say north of, or any type of geometric relationship, because it covers the whole geometric space that we are using to order our objects in that geometric space. So that is an idea of a global relationship. The idea about that is when you start looking at these specific relations and how they map in the structured graphics, you want to see if you have a single thread, if that relationship generates a single thread, or if it generates multiple threads, or could generate multiple threads and pathways through the structured graphics. What we would find with, like, the north of, you would expect a single thread of relationship through the structured graph.
Okay, so that's another question, is your use of the word thread. So I'm not sure I'm understanding that.
Okay, so we'll need to define that. It's just basically following the chain. I believe it's the term that Warfield used, but once you make a connection, you're connecting between the objects, you're looking at a structured graph, you just trace the connections through the graph. If there's only one pathway, if there's just a single pathway through the graph, beginning to end, is there multiple pathways? Are there branches? You can trace different threads through those pathways on the graph.
Okay.
I'll make sure we get that defined.
Okay. So I guess early on you said that Warfield identified 6 categories of relationships: definitive, comparative, influence, temporal, spatial, and mathematical. I don't think you revisit that set of categories. I was wondering if those related to the global-local distinction.
I haven't mapped those for the global-local distinction, but I'll take a look at that.
Yeah. The comparative seems the object-based and then spatial space-based, but yeah.
So one of the key factors for me, of course, when I'm looking at this is that I know that the reflexive logical property will have no impact on the thread, right? Because it only refers to one object. So it's not going to impact the connection between two objects, and the thread is basically following the connection between all the objects. The symmetric property will have an impact, and what it seems to me currently is that an asymmetric type of relationship, natural language relationship, tends to generate a global type of property, whereas a symmetric type of natural language logical property tends to generate a local type of property. And so those are the things that trying to discuss here and formalize those just a little bit more, see if those can be categorized that way. If they can, what are the rules that say, oh, well, given this context, then you can do this. Given that context, then you have to do that. And look at the processing rules that you would use to determine which one of these methods you would use. But that's kind of where we're going. So hopefully that helps a little.
Yes, definitely. Yeah.
Okay, we have about 4 minutes left, and we're not through. So we're going to go over a little this time. That's going to be, if people have time to stay. So the open source web applications, we talked about those. We should, as Mary mentioned a little bit earlier, we had some snafus with our connection to the internet, so it's not completely up to date yet. It should be up to date in the next couple of weeks, but if anybody wants to use that material before then, probably should let me know. We can make sure you have the current material. And then we just give a graphic here on the web application interface. And this one has both the strict order, which is manual, which you would do for developing an algorithm, and then the automated one, which automates the swapping, which takes a lot of the steps out so that it's reduces the chances that you will create errors. Okay, then we went through the handbook on interactive management, and the exercise here was to try to focus on which of the application structural types had a very close or a one-to-one relationship to the matrix types that are discussed in the mathematics of structure. And we defined I think 5 of them. Yeah, we identified 5 of those application structure types that have a very close relationship to the matrix types, and we decided to focus on those next to start developing a better definition and reducing uncertainty. So we went through and outlined what those were, questions you would ask, how you would figure out how the logical properties are applied in each one of these cases. Put in some comments here about exactly how these are interpreted. In the natural language interpretation, I think it's, as Kevin has pointed out, there's a lot of judgment involved. And so that needs to be clear how to do that. The thing that I also thought was interesting was the interest of the psychologists like Michael Huggin in Ireland, basically, that says, well, we really need to understand the capacity of the human mind to grasp these things. And we're not just overloading everyone with mathematical concepts that no one understands. And so this is where the computer comes in, not only for the calculations, but also the graphics, the colors, the shapes. And that's kind of the reason, the foundation, developing a foundation to go forward with that. And where you would actually maybe define tests, where you would test an individual to see how they actually view these types of logical relationships. I don't know if anybody, so these structures that some of them I was familiar with, some of them I'm not quite, but they're all of these matrix structures right now seem to have an impact or a discriminating feature that's associated with the threads through the model. And we'll try to develop that more as we go forward. And so then we talk about the mathematics of structure here, the reachability matrix. And then we introduce the natural language based matrix. And the reachability matrix is going to be the focus for next month. And what I'm doing there is I've defined what I called an enhanced reachability matrix, which then has a name tag associated with the reachability matrix that allows you to know what the natural language logical relationships were from the relation that created the reachability matrix. And you do that because the reachability matrix itself masks the reflexive property because it has all ones on the diagonal. So it could be, you could have this a reachability, you could have a single reachability matrix that was made from 3 different types of natural language relationship groups. And so what we're doing now with the enhanced reachability matrix is we're creating an encoding that's based on the AMEI that allows you to tack that information on. And so if I have this specific kind of reachability matrix that came from a different type of natural language relationship, then I could have an intelligent agent that would select on that particular logic that's associated with the natural language. So anyway, that's going to be the whole focus of next month. We're writing that up now, putting the math with some of the code with it that goes with Sage Math, and that's kind of where we are with that. And then here, kind of list what some of the uncertainties were, why we decided to encode that. Inclusion matrix has some of the same issues that the reachability matrix does, same with the subordination matrix. But what we've decided to do is do the reachability matrix first. Based on that, then address each one of these others so that we can have a more well-defined connection between the natural language structuring relationship that generated the reachability matrix and the reachability matrix processing. So if there's certain things about the area, the natural language area that generated this reachability matrix that are important in the processing, we now are going to have name tags on that reachability matrix that says, oh, you need to do these things to keep it aligned with the natural language relationship. Okay. And then we talk here a little bit about the adjacency matrix. And it's just, it basically is based on a graph of some kind. And without a graph as reference, it, could basically represent anything. The implication matrix, this is another one where it's very important in the reduction of computational effort. We've ran into some very interesting things about this algorithm that was encoded when we tried to duplicate the ISM software commands from the handbook. So we'll be talking about that later on after we get some of these other preliminaries done. But so far I haven't found a implementation that appears to follow the scanning method for the implication matrix, which I find interesting. It's because it has certain implications. So anyway, summary and conclusions, just the isomorphic models and creating more well-defined context that we can use to reduce uncertainty and therefore reduce complexity. So, and then references. So we'll take about, what, 5 more minutes, and people have more questions or other things you'd like to briefly talk about?
I'd just like to say thank you again for putting this together in this way. It's very helpful.
Well, yeah, I think we're getting to a point where we're going to be able to, let's say, increase our communication, our precise communication, and that'll be fun.
Yeah, I would like any references to where you build your language from natural language processing. That would be helpful. I think the
Peter, I think what we need to do. Let's see. Let me bring this other thing up here, and I'm going to share the screen application window back over here. Let's see. Right. All right. So have the agenda up. You should really join this structural modeling googlegroups.com group.
Yeah, I'll do that.
I've put some of that information there. I will send that information to you. Kowalski has a PDF of his book that I referenced there, talked about it, and it's clear. It's becoming, let's say, yeah, it's clear that there's conflicts within the logical application of structural modeling at the level it's developed now. And we can develop it so that those conflicts are defined and you have rule-based systems that address those conflicts. And to do that, we're going to need to integrate intelligent agents and logic. So I think that's what Kowalski does, and his whole thing is on natural language doing that. They have an open source tool, which is adaptive logic programming. And they've done a lot of research about the natural language interpretation and the confusion of logical abduction and causation and how these things can be addressed. So
that's very helpful, particularly to make some commentary or distinctions or relation to causal diagrams and system dynamics, or to
right. Systems dynamics is going to be over in the symmetric side or non-symmetric side, and that's exactly right. Causal loop diagrams is where we'll be.
Right, because I'm just seeking ways to constructively characterize that causal loop diagrams and systems dynamics within the domain of discourse about systems.
Well, I think Kevin was the one that brought up the fact that structural modeling was perceived as a precursor to the types of causal loop modeling, because structure and then causal loop modeling is process, right? The process part. So, and I did find that in one of Sage's early books, he talked about structural modeling being viewed as a precursor to the types of process dynamics.
Yeah, but so I think where you're going is how can I describe it? It's not a precursor to that. It is a transformation, possibly.
Well, yes, it's a little more
nuanced.
Well,
artistic.
Better defined.
Better articulated.
Better articulated.
Better defined. Okay. Well, any other comments, questions before we sign off?
Yeah, I still don't understand. And of course, I was getting my adjacencies confused there. The adjacency matrix, as I am familiar with it, is the fundamental matrix that one starts with, and the fact that it only speaks to whether things are connected. And so then they, in the model exchange isomorphism, there is always a graph that can be represent an adjacency matrix, and there's always an adjacency matrix that can represent a graph. So I really like your analysis of the different kinds of matrices here. I don't understand the need to define connected to, except as a natural language translation of mathematically adjacent in a graph to empirically connected to in some kind of study of some the interpretive side.
Well, Janet, I think that your point is really well taken, and I believe you're a mathematician. And so one of the things that's happened here is Warfield has also had a background in mathematics, degrees in mathematics, and what we're trying to do is clarify this natural language structuring model. So, and sometimes I like inclusion and influence or precedes or succeeds, things like that. Those are pretty much good natural language descriptions. Adjacency is not. And so what we're trying to do is reduce that uncertainty, to highlight that and say, okay, we want to pick a better natural language relationship that everybody understands besides mathematicians, what this means, and then we can use that. And when we translate it into the mathematics realm, then you can talk about it any way you wish. And so it's just to reduce the uncertainty and the confusion. So that's all. I agree with.
Right. I guess
with
if you treat them twice, then you get to show that for the math, there are not that many distinctions once you get to the mathematics. Once you get to that level of abstraction, you're dealing with binary matrices showing whether things are adjacent in a graph or not, and then the exponentiation of that matrix to reach the reachability matrix.
Major, right?
The inclusion as an interpretation of a reachability matrix, as you say there,
right?
And the subordination matrix again gets back to your point about the natural language reachability plus the identity matrix.
Right.
So there's a nice clean relationship between them all in the mathematics. That's actually simpler. But then once you get into so I just.
Well, you're absolutely correct on the standpoint of which of the mathematics to use. Once you get to the mathematics portion, once I'm ready to do my mathematics, it's ready, it's there, it's clear to the mathematician, right? Mm-hmm. But it's the translation from the natural language, structuring relationships, from ISM, the real world, non-mathematicians, we move those into the structural integration modeling, then that's where we're making this matchup. And as you pointed out, on the mathematics side, it's clear, it's logical, you can compute it, you're done, you get an answer, right? Mm-hmm. But changing, or what you have to do to a matrix to go from the natural language component and logical parts and move it to the math is really a rule set, and then the context and other things. And what we found was that the reachability matrix really didn't carry enough information with it about the natural language structural relationship to allow an intelligent agent to make decisions.
Mm-hmm.
So what we'll be doing next month is we'll be enhancing the reachability matrix. We'll be adding those name tags, those identifiers on there. And then it won't really be logic so much that makes those selections between, oh, what is the right type of processes, but more of an intelligent agent that understands what the correct transform is from natural language to the mathematics.
Mm-hmm. Mm-hmm. So it's an intermediate level, right?
Yeah, the SIM, the structural integration modeling, that's exactly what it is. It's putting these two things together in proper correspondence.
Mm-hmm.
When you put them together in proper correspondence, that's a rule-based type of intelligent agent.
Joe?
Yes.
Kevin and Peter have had a sidebar conversation on group chat that it would be good to read into the record if you'd like.
Good, go for it.
Okay, Kevin has said, Peter, for systems engineering, most all relationships employed are partial orders, such as the relationship function of. A partial order is irreflexive, asymmetric, and transitive. Peter comes back and says, Kevin, could it be then that because if that is the case for SE, then the variety is limited in the design and descriptions used by systems engineers? Kevin responds, possibly, that is the Simpsons' contention. They are familiar with math for dealing with non-partial orders. That's it.
Right. Okay, so all we've done is developed a rule, right? We've developed a rule that says, like, if you have two cities at the same level, right, then what we do is we don't use a partial order, we use a strict order, and we just order the equivalence classes. We're not ordering the cities like you would in partial order. So we step past the cities and we say, now we're just going to order these equivalence classes. And that's a processing rule that we use to simplify it. But yeah, that's exactly kind of what we're doing here. And we're
So I have to ask a question here. In what Kevin was saying also. So we're talking about strict versus non-strict order and partial versus total, right? Non-strict order is less than or equal to. Partial order says it doesn't necessarily apply for all of the pairs. And maybe that's your local versus global.
No, it's they're all connected, and I think that you're definitely right about identifying these are the issues we're talking about, and we can.
Yeah, that's a good topic for next time.
Yeah, but the idea is when you use like less than or equal to, this, and in summation here is the fact that less than is asymmetric, equal to is symmetric. And so you only have one at a time. Within our process, we go get empirical data. We go get this empirical data, and so we know whether it's equal and we know whether it's less than. So we don't need that if statement, because we just need a way to treat the information that we now have. And when we take the information that we get and we have to put it into a mathematical format that has the if statement, we believe it generates conflict and confusion. So we haven't used that yet. That's basically it. So we'll get some rules and get it going. And
right. Well,
look at
the paper is wonderful contribution. Have you heard from Caesar yet?
We will be. The paper has been accepted.
Good.
And so we'll be seeing how that works out and just going forward from there.
Yeah,
so
because I think if you have these technical papers to refer people to. This is excellent summary to get people up to speed.
Yeah, we'll be doing one of these every month now to support the video conferences, and we'll be doing try to get them out a week to 2 weeks ahead. But be sure to sign up to the structural modeling Google groups. That's where all this information we're going to keep there. So all our daily ideas, wild, information, or just whatever is the current, and then we'll work that up and refine it and get it out in the technical report.
Very good.
Kevin added a final note on his statement. He says, but if something is not a partial order, then first order logic does not apply.
Well, I think we should defer that statement.
Right. Yeah.
Let's defer that for a while.
Yeah.
And we'll think about that.
Partial orders are definitely the preferred theory of logic.
Well, we're not saying that. The only thing we're saying is we don't see why we need to use them.
Right. And then,
because they introduce uncertainty, right? They have an uncertainty rule in them.
right.
And so when you introduce that uncertainty, you introduce complexity. And so our goal is to say, well, we want to reduce that uncertainty so we can reduce the complexity. So far, we believe we've been able to do that.
Right.
Okay?
Good.
Well, it was great talking with everybody. And again, be sure to sign up for the structural modeling Google groups. And we'll get some more stuff on the wire in a couple of weeks.
Okay. Very good.
Take care.
Bye-bye.
Bye-bye. Thank you very much.
Bye now.